Hi, my name is Kang Zuheng from Ping An Technology, and I'm happy to present our paper, SVVAD, which is a personalized voice activity detection method specifically designed for speaker verification. Let's start with a little background and then understand the motivation for our new VAD. VAD is a way to distinguish speech part and non-speech part, then to remove the non-speech part. Long ago, we used this algorithm for speaker verification, but this method is not good because it can't distinguish the voice from other speakers. So someone developed personalized VAD. This method can further distinguish the voice from the target speaker and non-target speaker. Look at the green block. The non-target speaker's part is also found out and removed. So this method is better for speaker verification, but it is still not optimal. Now someone may ask why this method is still not good for speaker verification. What exactly leads to the performance improvement? Here are a few examples. The target speaker's speech may be corrupted by a lot of noise, or the other people are talking at the same time. These cases may lead to a big performance drop in the speaker verification. As we know, the SV models are noise robust. When we meet a lot of noise during speech, we need to suppress it. However, the speaker verification model can't handle non-target speaker's voice. We should mask out this part because it affects the performance a lot. There's another example. Previous VAD models are trained based on strong labels, but these labels are usually human design and not accurate. Also, the traditional VAD will remove the invalid part and then concatenate the valid part together. Here may exist the breakpoint in between. This also leads to the performance drop. In summary, we need to design a new VAD that meets two requirements. First, VAD labels should be soft labels, not hard labels, because each frame have different degrees of contribution to speaker verification. Second, this VAD label cannot based on human intuition, but should be decided by the speaker verification model itself. With this in mind, we designed a new VAD framework called SVVAD. The SVVAD has two goals. First, each frame will save or block with soft labels, rather than to remove them with hard labels. Second, these VAD labels should be generated by speaker verification model, but without human labeling. For the first goal, the soft label can be achieved by this formula. For each frame of T, the VAD model will calculate two values, gamma and beta, as our VAD decision. These two values will modify the original speech information, x of t, to the new speech information, x of VAD. In simple terms, if gamma is 1, this information will save. If gamma is 0, this information will be blocked. If beta is larger, this information will increase. Otherwise, it will be suppressed. This is how it works. For the second goal, to automatically generate the VAD label, we designed a special training method. Seen from the figure, we can know a few things. Firstly, the function of SVVAD model is to modify original male filter banks to the new male filter banks with our VAD decisions. Secondly, the target speaker's speech information will be used as a reference to the SVVAD model. With this, the model could know how to filter out the target speaker's part. Thirdly, the way to modify male filter banks is to calculate gamma and beta for each frame. To train this model, we use the triplet loss. Here, we input with the enrolled utterance with one speaker and tested utterance with multiple speakers. If the enrolled sample and tested sample contains the same speaker, for example, if the enrolled sample has speaker A and the tested sample has speaker A and B, here they have the common speaker of A. Then the model will narrow the distance of voice print vectors. Otherwise, if enrolled sample has speaker A, but the tested sample has speaker B and C, here they don't have the common speakers. The model will widen the distance of the voice print vectors. With this rule, the SVVAD model can automatically find out the VAD decisions for speaker verification. There is completely no human labeling. Since the original triplet loss is not optimal, we designed 4 types of losses by adding cosine distance and CCC loss. The inference process is pretty simple. We just need to input the enrolled voice print vector and the tested male filter banks into our SVVAD framework. Then, the SVVAD model will automatically modify the male filter banks and then calculate the voice print vectors for you. Finally, these 2 voice print vectors can be scored by cosine distance. Now let's see the experiments. Firstly, we will learn how to build our training data. Step 1. We use the public VoSleep 1+2 dataset. Step 2. We directly use the audio from the dataset as the enrolled utterance with one speaker. Step 3. We can build the test utterance by concatenating speech from different speakers together. Step 4. We will then apply augmentation with noise and reverb to this audio. The evaluation metrics are similar to speaker verification. Here, we use the EER and mean DCF for evaluation. Here, the big table shows the overall comparison of speaker verification performance using different methods. There are 3 baselines and 4 types of triplet-like losses. We can see that, first, our SVVAD framework can improve performance when mixed with non-target speaker's voice. Second, the triplet loss plus CCC performs better than other methods. As we know, the speaker verification is scored by cosine distance. But why adding the cosine distance perform worse? From our analysis, the voice print vectors contains hundreds of values, but the cosine distance only has 1 value. It is really hard to train only by this value because it's too implicit. But the voice print vectors have more values, so it's much easier to train. This is why it performs better without cosine distance. To improve the performance, here we combine 2 types of losses, with or without the cosine distance. From the table on the right, we can see that, firstly, the triplet loss plus CCC and the triplet loss plus CCC plus cosine distance performs the best. Secondly, from the red box, we can see that the performance changes little when testing with only one speaker's voice. In summary, our SVVAD framework can greatly improve the performance of speaker verification when other people are talking, but without changing the original performance. From the t-SNE plot, we can see that after using SVVAD, the dot is more clustered. This also validates the effectiveness of our framework. Also, we have 2 samples that could be here.
Raw audio. dans sa tête. En fait, lui, il est très amoureux, il n'y a pas de problème, il adore sa Julie.
Got a chance to sit down with Justin Verlander to talk salary, golf, and gay rights.
VAD audio.
Dans sa tête. En fait, lui, il est très amoureux, il n'y a pas de problème, il adore sa Julie.
From this, we can hear that our model can block non-speakers' part by adding s among them.
Raw audio.
Dans sa tête. En fait, lui, il est très amoureux, il n'y a pas de problème, il adore sa Julie.
VAD audio.
Dans sa tête. En fait, il n'y a pas de problème, il adore sa Julie.
From this, we can hear that the model will suppress the noise part when it is too strong. These samples matches human perception. So in conclusion, we demonstrate that our SVVAD framework can make speaker verification system more robust when in noisy conditions and mixing with non-target speakers' voices. We designed a label-free training method with 4 types of triplet-like losses. The experimental result shows that our SVVAD framework outperforms the baseline in EER when in noisy and multi-speaker conditions. The 2 audio samples show that the decision of SVVAD matches the human perception. Thank you for listening. If you like our paper, please cite us. Thank you very much.